Hello, and welcome to this video on graphing sine and cosine using transformations with a specific focus on changes in the period. Okay, I said I was going to make a video that just focused on that, and here it is. So when we talk about, we're just focusing on period, we won't be talking about vertical stretch or compression or reflection. We won't talk about horizontal shift. We won't talk about vertical shift. Okay, now we're under a couple assumptions here for prerequisites. Okay, one is that you have the parent functions committed to absolute memory for y equals sine theta and y equals cosine theta. Okay, now you also have to know their graphs, their tables pretty well. Okay, these tables are important. They're just the representations in discrete form of the graphs. Have to have that. Another thing you need to be able to do is be able to understand the standard forms of sine and cosine. Now, that should be decently fluent because if you're a Springfield Township High School student or have been one of my students, we tend to introduce all transformations with the parameters of a, b, h, and k. So it shouldn't be much of a leap. When you move over to here, same thing is kind of going on, except the input is theta as opposed to x. Okay? You have to be able to be good there. You also have to understand that period can be computed by a formula for sine and cosine functions of 2 pi over b. You have to comprehend what period means. Okay, so that being said, going to do this two different ways, and right now you should be seeing sort of two timeline markers that you can fast forward to either one of them if you'd like for comprehending which method you want. Good for this video if you're watching the first time, watch both. You're then going to need to pick a method to be able to go with, and if you need to rewatch it, use the timeline markers here to get to that method. Okay? I will tell you this. I think you become a better trig student for understanding this bottom one. You are not unsuccessful if you're using the 1 over b method. That is what you've done all the time in dealing with transformations, except when you do it, you're not really kind of doing it with a priority and understanding period. You're sort of getting it sort of as a byproduct of doing it kind of an old school way. Okay? So real quickly, I just want to take a quick review of being able to identify these standard forms here. So if we look at this function, y equals 2 sine of the quantity 4 times the quantity theta plus 1 minus 3. Quick A, B, H, K chart, just to review quickly. A is 2, B is 4, H is negative 1, K is negative 3. Okay? Now, I'm not going to focus much on A, H, and K here because they create vertical stretch and compression as well as horizontal and vertical shift. We really are trying to focus here on the parameter of B and how it affects a change in period. Well, this first method that I'm going to do will just rely on what you've done in times past. If you say b equals 4, you're going to multiply the inputs, in this case they're the theta values, by 1/4. Okay? It's the 1 over b method. It really just uses the reciprocal of b and multiplies, and you get the inverse effect, just like you always have. Okay? You can start with the parent graph, change the input values by that multiplication, and the period will magically happen. Okay? So I'm going to go to some examples of that to start, and we'll take a look. So using the 1 over b method to graph y equals 2 cosine theta. Well, if I make an ABHK chart, which is always a great way to go, we see that A is 1, B is 2, H is 0, and K is 0, and there's no shock that those parameters won't create change here because I said I was not going to focus on that. So if b equals 2, we're going to multiply the inputs by 1 over 2. Okay? The inputs being the thetas. Again, we talked about the fact that you really need this chart committed to memory. Okay? I actually could start with the parent points up here on the graph. Okay? And if I wanted to, that's sine. For cosine, they would look like this. And I could work them from the graph, but I'm just going to work them from this table so it puts a little more focus on the table. Okay, so what am I going to do? I'm going to multiply all these by half. So now I get half of 0 is 0, half of pi halves is pi quarters. Half of pi is pi halves. And then half of 3 pi halves, just to draw up the margin so you see it, is 3 pi quarters. When you take half of a fraction, you double the denominator. Half of 2 pi is pi. So now if we go to make that graph, we would get the transformed input values, and we would see you'd get 0, 1, pi quarters 0, pi halves negative 1, 3 pi quarters 0, and pi 1. So that's one cycle of that graph. Okay? Now, I didn't put the parent points up for this because multiplying them from this chart is completely legitimate. Okay? If I started with the parent points on the graph, I would get the same thing. And I'm just going to move this over here to show you that I'm not getting any different answer. Let me group it and move it. Okay? And if I started with the parent points, they would be starting at 1, going a 2 pi cycle, okay? Having those committed to memory. Those points are, in fact, the ones written in black inside that blue box I just boxed. And then if I did it from the graph, it's just a matter of reading correctly and saying, well, the input here is 0, cut it in half is 0. The input here is pi halves, cut it in half is a quarter. The input here is pi, that makes it pi halves. You could also use the number of grids and say you've got 1, 2, 3, 4, 5, 6 grids. So cutting that in half would be 1, 2, 3 grids. And then half of 2 pi for this point where the input is 2 pi would be pi. Now if you notice, doing it on the graph, you get the same exact thing. Okay? So if you're starting with a chart, you can just multiply by the reciprocal of b for the input values, create new input values, and there you go. Easiest way to do it. Don't forget, though, if you're asked to make 2 cycles of the graph, that you, in fact, repeat it. I know you can't copy and paste it on your paper, so there we go, just for the sake of time. Okay? And I will just make it dotted so you see it's a second cycle. Now, getting back to looking at making a sine or cosine graph using the nature of period length, I'll just come back to this original slide just to take a quick look at how to use the period formula. Okay? And we see here it's dependent on understanding what b is, so b is still equal to 4. I haven't changed anything here, okay, from this function. So now that means I'm going to get 2 pi over the absolute value of 4, which is pi halves. Okay? So the one thing you could comprehend very quickly from that is if I made a sine graph, which kind of looks like that, the distance from start to finish is pi halves. Well, comprehending that and applying that to make a graph are two different things. So I want to give a little more investigation around the geometry of this shape here and give you a method for being able to make that graph without using parent points per se. Okay? That you'll be able to say, I understand how the parent points are transformed without putting the parent points on the graph. Okay? Now to do that, I just want to go over to a Sketchpad demo and give you a little bit of time there with that. Okay? So, what we have here is sort of a dynamic demonstration of using a sine curve with changes in the period. So, if I showed you the basic sine curve with a b value of 1, okay, and you'll see it up there in the function. Try to see past the x minus 0 and the plus 0, okay? Because they really just mean that that is y equals sine 1x. And then if you looked at the period formula, you would get 2 pi over the absolute value of 1, which is 2 pi. Well, if you notice, if I trace one cycle here, it goes from 0 to 2 pi. So this is not a shock. Okay? Now, similarly, if I change the b value to 0.5, okay, it's going to change the cycle length because it's creating a horizontal stretch. If I look here at the period formula, which is 2 pi over 1/2, which is 0.5, 2 divided by the absolute value of half is 4 pi. And if I trace one cycle of the graph, you'll see that's 4 pi long because it starts at 0. Okay, so we see that the formula is reliable. Now, a couple things you need to be able to comprehend about the formula, though, is how to sort of sit there and go, okay, I've used the formula to know the period length, but how can I actually sort of be able to make a graph quickly using it? And I think if we look at these things that I'll call quarter markers here, if you notice that, again, this one cycle, if I trace it, it has these 5 lines through it, but you see that it's actually split into 4 sections by doing so. The nature of understanding these lines, I think, and where their placement is, can help you generate a copy of this curve without necessarily using the parent points. Okay? So let's actually take a look here and see if we can develop another formula for understanding this distance, okay, what to count by there. Okay? So let's hide these quarter markers here for just a second. And keep in mind, if we're splitting it into 4 sections, there's maybe something about dividing by 4 that's going to help me do this. Okay, so let's actually do this now. Okay, let's actually make b equal to 2. Okay, so the period is going to be 2 pi over 2 in absolute value. So period is pi. So where do the quarter markers come in? Well, if we're splitting it into 4, the quarter markers can be found just by dividing the period by 4. Okay? So let's actually see that. The period is pi. We'll divide it in by 4 and talk about pi fourths. So I would be here, counting off by pi fourths. And then if I show the quarter markers, you'll see that they're in fact right on those points. And why are they important? Well, because they would then tell me, knowing the general shape of the parent curve, that sine starts at 0, it comes up to 1, back to 0, down to -1, and back to 0. Now, if I just understand that shape, which I'll kind of freehand down here for a second, know the width, and know how to split it up into 4 pieces, I could draw it without ever drawing the parent function. So I'm actually going to attempt to do that now. But what I'll do is I'll actually hide the function. And then what I'm going to do next is pick a b value again, which is 0.5. Now the graph is just invisible. So if you notice, the period's going to be 2 pi, excuse me, I hadn't erased that from before. It's going to give you 2 pi divided by a half, which is going to give me 4 pi, right? And then these quarter markers I'm talking about would just happen at the period divided by 4, because I'm splitting it up into 4 pieces. So if you notice now, every pi I would be getting a quarter marker. So I would just sit here and go, okay, here, then at pi, then at 2 pi, then at 3 pi, then at 4 pi, and I know to stop there because that's the period length. Now I could sit here and say, okay, now I just need to kind of put the sine function in, and what do we have here is at 0, it's 0, At the first marker, it's 1. At the second marker, it's back to 0. At the third marker, it's down to -1. And at the last marker, it's back to 0. And then if I showed you the plot, it would fit that. Again, this is a great way to sort of understand how to start the drawing of the function using the period. Now you have to understand the b value when we did it in transformations was always the hardest. So it's nice that you kind of almost get this out of the way by doing that. So I'll show you again on doing the quarter markers. Let me get a little erasage here first. Okay, on another value of b. Okay, don't want to erase this quarter marker formula, which is what? The period divided by 4, because you're splitting it into 4 major parts. Totally works for cosine too. Okay, so I'll hide the graph, reset it. I'm going to get a b value of, let me try and get a quarter, 4 here. Okay, b is 4. So now I know that the formula for period is 2 pi over 4, which is equal to 2 pi over the absolute value of 4, which is pi halves. So now if I go to do the period of pi halves divided by 4, that's going to give me pi eighths. And if you don't understand how to divide fractions, that is not good. Okay? So pi eighths is a little tricky to find on the scale of the graph, but I'll just count by pi eighths until I get to pi halves. Okay? So it should be pretty cool. I'll start at 0 with a quarter marker. And then I said I'm going to go to pi halves, which I'll note that to start. Okay? And now I've got to count by pi eighths. So you've got pi eighths, pi quarters, 3 pi eighths, and then hopefully when I show the graph, after I put in the appropriate sine curve, it'll be correct. Start at 0, go up to the 1 for the second marker, come back to 0 for the third, go down to -1 for the fourth, and finish on the fifth. So, if I've done this correctly, absolutely works, even as tight as that is here. Now, if you're not on graph paper, you can create a scale that's much more pleasant. Okay? So, what have we talked about here? Understanding the period is about 2 major things. A formula that computes the period, and then knowing how to slice up that period by using another formula here, and then just saying, I'll make a graph that is the general shape of sine using that period length and knowing where to put the interim markers. Okay? So, let's try and put that in action now, not with this Sketchpad demo, okay, but with just a normal graphing window, okay, with graph paper, get to work and see what happens. Okay, so now you've got the function y equals sine over half theta, okay, and you're going to use the periodic nature of the function, okay. So I hope what you realize is you're not going to use the parent points. You're going to use the adjusted parent points on the period, okay. So I'll put them in this chart to start, and then I'll label them up on the graph paper. So I see here that my ABHK chart is going to be A is 1, B is a half, H is 0, K is 0. And you're not interested in A, H, or K in this video. Okay? So if B is a half, I'm just going to plug it in my formula. It'll be 2 pi over absolute value of a half, and see that my period is 4 pi. Okay? Now if the period is 4 pi, the quarter markers, okay, lack of a better word, can always be found by the period divided by 4. So that's 4 pi over 4, which is pi. That means I'm going to count by pi till I get to 4 pi. So I'll start with 0, pi, 2 pi, 3 pi, 4 pi. And why are these points here? These points are here because, again, like we said, they're the sine points. So what do I know? I know I'm going to be 0, pi, 2 pi, 3 pi, 4 pi are the markers. And then I need to just realize that putting the output values in that are appropriate as sine starts at 0, goes up to 1, comes back to 0, goes down to -1, and finishes at 0. And this is, in fact, one legitimate cycle of y equals sine half theta. And again, notice I did not start with the parent points. I actually used the nature of period, understanding to split it up geometrically into 4 pieces, throwing it into a table, and then using the output values for sine that I always have. Totally legit. Again, the parent points that I did not start with, here I'll just do them lightly in yellow, are here. 0, 0, pi halves 1, pi 0, 3 pi halves -1, and 2 pi. That one cycle I did not need to start with. To do, what you should expect is a horizontal stretch by a factor of 2. Okay? I get that effect by just using the period formula. So, I hope this has been a help. What you need to be able to do, though, is be able to sort of integrate this into transformations that also have vertical stretch, also have or compression or reflection, along with horizontal stretch, horizontal shift and vertical shift. I just want to take a quick look here at a problem without really doing it that would talk about doing that. So if you had 2 sine 1/2 theta minus pi quarters plus 2, you would make an ABHK chart. Okay? A is 2, B is 1/2, H is pi quarters, and K equals 2. The batting order of this really becomes important. You really should be trying to make sure by the order of operations you apply your parameters of A and B first, followed by H and K second. So, if you are using the periodic nature of the graph, or even if you're doing 1 over B, I would start with trying to get the nature of the horizontal compression or transformation done first before the vertical stretch, okay, or compression. So I've shown you how to do period 2 different ways. I haven't shown you how to do an entire graph together. That's for you kind of to work out and put together a little bit. Might make a video on that, might not. So I tried to give a lot of focus here on how to deal with B, and we showed it 2 different ways. Okay? So when you're trying to put it all together, just make sure that you're trying to go in a good order, which is probably apply B first, because it's the trickiest, then A, okay, and then do your horizontal and vertical shifts. So I hope this was a help. Enjoy, practice, share.